was wondering, could you help me out with mechanics? I think I kind of get it, but I have a bit of difficulty when I'm trying to solve problems.
Okay, sure. Let's do an example. If I take this textbook and I move it across the table at a constant speed, can you tell me what's happening in terms of forces? What forces are there?
Well, there's the force of your hand, obviously, pushing forward on the book. And then there's the force of gravity down, because everything is attracted towards the earth. The table counteracts that and puts an equal force up. And then there's friction, which is pushing back on the book.
So why does the book move at a constant speed when I push it across the table?
Well, the forces of gravity and the table are balanced out. So that must mean that the force from your hand is slightly greater than the force of friction backwards.
What would Newton's first law say about this?
Well, an object moving with constant velocity keeps moving at that constant velocity until it's acted on by an unbalanced force. That's Newton's first law, right?
So what kind of motion is the book in when I push it across the table?
Well, it's moving at a constant speed in the same direction. So it's moving at a constant velocity.
So are there any unbalanced forces acting on it?
Well, I guess not then.
Right.
So that means the force from your hand is exactly equal to the force of friction.
Yeah.
But the forces weren't always balanced, were they?
What do you mean?
Well, when you first started pushing the book, it went from rest to some constant speed. So that means it must have accelerated. So the force from your hand must have been greater than the force of friction, at least to start with.
Yeah, you're right.
It's just weird that you don't need an unbalanced force to keep something moving. I mean, that's what I always thought. Wait, so when you're not touching the book, there are no unbalanced forces on it, right?
What do you think?
Well, I know there aren't any unbalanced forces, and the book just sits there. So why doesn't it keep moving with a constant velocity?
Well, 0 is a constant velocity, isn't it?
But if I push the book and let go, it would eventually slow down and stop.
Well, that's because of friction. It's easier to see if you take friction out of the equation. Like if I put this slider on an air track, you see that whatever its motion, without any unbalanced forces, it continues at a constant speed. Could you show me what a velocity time graph would look like for the slider?
Well, hang on, can you explain velocity to me? I mean, you've been using the word speed a lot. It's moving at a constant speed. I know what that is. Like if I walk through 1 meter a second, I'm moving at a constant speed of 1 meter per second. So how's velocity different?
Well, velocity is just speed with a direction attached, like 1 meter per second north or 2 meters per second up.
Well, that's all right then.
Now, can you draw me a velocity time graph for the slider?
I think that would look like this.
Okay, but if I read off the graph, then the velocity here is different to some other time.
That's just a silly mistake. I've drawn a position time graph. So a velocity time graph would look like this.
Yeah, that's right.
Oh, good. Well, I think I've got that now, but that's just a really simple example. I mean, my exam isn't going to be all about books moving at constant speeds across tables. How about we try something else?
Well, Luke's juggling outside. Let's see if you can explain that to me. Can you tell me what happens when a single ball goes around once?
Well, Luke's hand gives the ball a force that drives it upwards against gravity. But as it goes up, this force gradually dies away until at the very top it perfectly balances gravity. And then gravity wins and the ball falls down.
You said that at the top, the force from his hand and the force of gravity are equal.
Yeah, that's right.
So why doesn't the ball keep doing what it's doing, like in the book example? No unbalanced force means it moves in constant velocity.
I don't know, actually. I mean, maybe it's air resistance, but... Oh, well, it's only balanced at the top for a second, but... I don't know, I must be missing something.
I think now's a good time for Newton's second law.
You mean F equals ma?
That's the one, but can you tell me what it means?
Well, Newton's second law says that any unbalanced force on an object will cause it to accelerate in the same direction as the force. And the bigger the mass of the object, the smaller the resulting acceleration from the same unbalanced force.
Does that make sense to you?
Well, yeah. I mean, it's easier to accelerate a tennis ball than, say, a lead weight of the same size.
What does Newton's second law say about velocity, though?
Well, it doesn't really say anything about velocity. It tells us about acceleration, which is the change in velocity.
So when the ball's going up, is its velocity changing?
Yes, it's slowing down.
And which way's the acceleration?
Well, down, so it's opposite the direction of motion.
And when the ball's falling down again, is its velocity changing then?
Yes, well, it's speeding up this time, so the acceleration is downwards, in the same direction as the motion.
So by Newton's second law, which way is the force on the ball?
Well, down. It's just the force of gravity.
Good. What about at the top of its flight? What forces are acting on the ball then?
Well, none. I mean, it's not going anywhere, right?
But just before it reaches the top, which direction is it going?
All up.
And just after?
Down.
So when the velocity is zero, could it still be accelerating?
Yes. It's accelerating downwards. It's just weird to think about it, that velocity can be changing even if velocity is zero. But I guess Newton's second law doesn't tell us anything about velocity, it tells us about acceleration.
Good. When the ball's in the air, what forces are acting on it?
Just the gravitational force downwards. It has the same force acting on it, and so the same constant acceleration at all times.
Good. What about when the ball hits Luke's hand?
Well, first he catches it, right? So his hand puts an upwards force on the ball. And this force has to be greater than the force of gravity down. So that means there's an unbalanced force upwards, and the ball accelerates in the upward direction.
Right.
So he applies this force and the ball slows down, and its velocity goes through zero. And as he continues to apply the upwards force, the ball's velocity increases in the upwards direction. And so he lets go.
Good.
Okay, give me another example.
How about a kite on a ramp?
Now that's a bit more complicated, because now in addition to the force of gravity down, we've also got a force from the ramp on the car. But this only cancels out some of the gravitational force, which leaves a net force down the ramp.
So what happens to the kite?
Well, if you let it go, it accelerates at a constant rate down the ramp.
Does the unbalanced force on the car change?
No, I mean, that depends on the steepness of the ramp. So if the ramp is at the same steepness, the unbalanced force is constant and down the ramp, so velocity will increase linearly with time.
Can you graph what you mean by that?
Sure. I think it looks like this.
Right. What if now we give the car a push at the bottom of the ramp and wait for it to come back down?
Wait, so you're saying it starts with some speed up the ramp?
Yeah. What about the forces?
The force doesn't change, actually. It remains constant and down the ramp. That's why the car slows down as it goes up the ramp.
What about at its highest point? Is the force zero?
No. Even though the velocity goes to zero, it's still accelerating down the ramp. That's why it speeds up as it goes back down.
Absolutely. Could you make me a velocity time graph for this?
I think it would look like this. The car goes up the ramp, turns around, and comes back down.
That looks like the path the car traced down, rather than a velocity time graph.
Ooh. So is there something wrong with that picture?
You tell me. When is the velocity zero?
Well, according to my graph, it's at the start and at the end of the trip. But, wait, that's not right. I mean, the car started with some speed up the ramp, and then it's ended with some speed down. The acceleration was constant, as we agreed, So the correct velocity time graph would look like this.
Right. I think you've got Newton's first and second laws down.
Yeah, I think I feel a bit better about mechanics now.